Welcome to this lecture series in linear algebra. In this lecture, we look at the notion of orthogonality in the context of bilinear forms. And let us recall some of the things that we need. So suppose f is a bilinear form on a vector space V. Then we saw that we can define these two maps. The first one is nothing but u going to fu blank. And recall that this is a member of this space, which when you feed little v2, it outputs this guy. Similarly, we can define this, which is v going to f blank v. So we have those things. And now we may define the rank, or we define the rank of the bilinear form as the rank of either of those things. So we proved that the rank of this and the rank of that are the same. In fact, we saw a way in which these two maps are actually the same, because once you take the transpose of, I shouldn't say these two things are the same, they are in some sense, the transpose of this is some sense the same as this map. In which sense? So what you do is you take the transpose of f, you get a map from v double star to v star, and now you use the identification between v and its double dual and take this composite. This happens to be rf. So this is what we saw, and therefore these two ranks are equal, and this is what is defined as the rank of f. And we defined a notion of non-degeneracy. So we say that f is non-degenerate if the rank of f is the maximum possible, otherwise we call it degenerate. And another thing we saw is that if we have a bilinear form on a vector space V, then we may restrict it to a subspace and get a bilinear form on the subspace. So basically what I'm saying is you can get this map. Then we have this map, f restricted to w cross w. Is in the space of bilinear forms on W. And this is written as, this is a fine notation, but just we will abbreviate this as that. Okay. Also recall a notion that we have dealt with way earlier in the course. So if W is a subspace of a vector space V, then the annihilator of W is defined as all those linear functionals on V such that they kill everything in W. And we saw that the dimension of the annihilator is the dimension of V minus dimension of W. So we will use these facts. These are two problems for practice. And now let us get started. So we will make a very, very simple observation to begin with. So suppose f is a bilinear form on V and W is a subspace of V. Then what we can do is we have W, and we may first take the inclusion map into V. So this is the inclusion map which takes W to W. Of course, this is a linear map. Okay. And then we may apply LS to move to V star. And then we may apply the transpose of the inclusion map. So let's denote the inclusion map by I sub W, and this is then the transpose of IW. And the target of that will be, of course, W star. So we get, these three maps, and we may take the composite. So this is the composite. All right, and what we want to say is that this is actually something that we have seen. So let's see what is going on here. So W is going to, so first, if you take a little W, it becomes W. Doesn't change, of course, it's the inclusion map. Then you get this dude, which is that by definition. And then you get, so then you apply the transpose of the inclusion, and the transpose of the inclusion is the restriction. So recall that if W is a subspace, then I transpose a map from V star to W star just takes a linear function and restricts it to W. So just recall this basic fact. And therefore, what we have here is the restriction of this guy to the space W. Okay? All right. So if you just think about it, this is nothing but, or maybe I'll use a different color. This is nothing but LF of the bilinear form restricted on W, right? So this dotted map that I've drawn is nothing but LF of the bilinear form restricted on W. So this is basically what I wanted to say. This is nothing. This is a very, very simple exercise. Okay? And similarly, you have a diagram for RF. It's the same diagram. Let's not repeat it. Okay, so once we have this observation, let's move on, and let me confirm that I do not want to say anything else. Maybe I should just maybe remind, I don't know if I said it earlier, but we say that, so F is a bilinear form on the vector space V. We say that F is non-degenerate on W if F restricted to W, this bilinear form, is non-degenerate. So we have extended our scope of non-degeneracy. In the recall, we defined the non-degeneracy of a given bilinear form, period. But now if you're in addition given a subspace, you may say that the given bilinear form is non-degenerate on that subspace if the restricted bilinear form is non-degenerate. And this does not conflict with the terminology that we introduced earlier, because F is non-degenerate is equivalent to saying that F is non-degenerate on the entire vector space V. So it's just an extension of the previous notion. Okay. So this terminology we have, and so let's move on. So now this is the main concept of this lecture. So suppose F is a bilinear form and we have two vectors V and V prime in the vector space. Then we say that V and V prime are orthogonal, and in this order, here the ordering matters. V and V prime are orthogonal, or more precisely, orthogonal with respect to F. So when we are dealing with a fixed bilinear form, there is no confusion. But if we were dealing with multiple bilinear forms, then we should mention, when we say orthogonal, we should mention with respect to which bilinear form. So here, since the bilinear form is fixed, I have put things in bracket. So we say V and V prime are orthogonal if this happens, right? So this is a natural definition of orthogonality. And maybe one example, I at this point, I do not want to give too many examples of this. When we will do inner products, things will be more clear. But as of now, let's just look at the most basic possible example. So you take your R2 as the vector space, and consider this bilinear form. We saw this example for a general n, so we have this example. And now what you do is, you take this vector, call it whatever, I don't know, call it V. Then you take anything on the line perpendicular to this line, and you will find that indeed those two vectors are orthogonal. Maybe let me call them v. Okay, I've called them x and y. So let's call this also x. So if you take anything perpendicular to this line, you will see that f of those two vectors is 0. And all I'm doing is just priming you for dot product. So in high school physics, you must have seen, or in mathematics courses also, you must have seen the notion of dot product. And this is precisely the dot product of two vectors, right? Maybe there's a normalization factor, some cos, or some normalization. I don't know. I don't remember how we defined it, but essentially this is the dot product. And that is why I say perpendicular. So just keep this example in mind. And here is what I want to note in the more formal way. So v and v prime are orthogonal if and only if v is in the kernel of Rf v prime. This is immediate because the reason is this. V is orthogonal to v prime if and only if this is 0 by definition, which happens if and only if f blank v prime of v is 0, which is same as saying Rf v prime when applied to v is 0. So that's the reason for this equivalence. And one thing I also want to note is that this is, here the order is important. So if you say v is orthogonal to v prime, in general, it does not mean that v prime is orthogonal to v. Okay, and here is an example. So let alpha and beta be in R, and consider this one. So we have this, let's say v is this vector space, R and X, and recall we defined this bilinear form, which takes px comma qx and outputs the product of the evaluations. Okay, and here you can see that x minus alpha is orthogonal to x, but x is not necessarily orthogonal to x minus alpha. So if you take beta different from alpha, here you take beta different from alpha, then this is not orthogonal. So it's a very simple example to show that this is not commutative. You cannot switch the order in general. Okay. Now for the notion of orthogonal complements. So W be a subspace of a vector space V, and F be a bilinear form on the vector space V. Then the orthogonal complement of W, again, when we say orthogonal complement, it is with respect to a fixed bilinear form. That is something that we need to be aware of. So the orthogonal complement of W is defined as, by notation, it is W, and then we make this superscript, and we read this as W perp. So this is read as W perp. Okay. So this is defined as all those things in V, such that so just give me a second. Let me not mess up the order. I just want to be consistent with the ordering. So this is all, let me change the notation also. So all W primes in V such that W is orthogonal to W prime for all vectors in W. So that's the definition. That's the definition of the orthogonal complement. And as for an example, you can just again repeat the R2 example that I gave. So here you take some vector fix, maybe this is your subspace. So not just a vector, you have an entire subspace. So this is W. I don't know if this line is even straight. Yeah, I hope it is straight now. So this is W, and then the orthogonal complement of W will be this guy, where of course I'm using the same bilinear form as in the last slide, the dot product one. Right, so all of these things will constitute W perp. Okay, and you can think about the higher dimensional versions. You can consider the same kind of bilinear form for R3 and there visualize what is going on. But for now, this is the only example I want to do. Okay. So let's make this small observation. W perp is same as this guy. So you take the annihilator and then the pre-image of the annihilator under this map RF. So this should be an easy exercise by what we have already noticed. So here is the proof. W prime is in W perp if and only if W prime is in, so it is in W perp if and only if f W comma W prime equals 0 for all vectors in the subspace, which happens if and only if f blank W prime of W equals 0 for all W in W, which happens if and only if RF W prime of W is equal to 0. And this is same as saying that RF W prime is in the annihilator of W. This is a linear functional which kills every vector in this subspace W, and hence RF W prime is in the annihilator in W, and conversely. So this is same as saying that W prime is in the pre-image of the annihilator with respect the pre-image with respect to RF. So it's just that, it's nothing. In particular, this implies that this is a subspace. It is a pre-image of some linear subspace under a linear map. So this is a subspace of the vector space V. Okay, thing. If F is a bilinear form, then rank of F is just the difference of these two dimensions. Okay, so let's finish this quickly. So V is in V perp if and only if RFV is in the annihilator of V, which happens if and only if RFV is 0. Because if you have a vector space and you take the annihilator of the entire vector space, you get 0. Nothing annihilates the entire vector space except for the 0 functional. So we have that, which is as good as saying that V is in the kernel of RF, right? And therefore, thus V perp is same as the kernel of RF, and thus by rank nullity dimension of V is the nullity of RF plus the rank of RF. I'll just write rank of RF but kernel RF is V perp as we saw earlier, saw here, and rank of RF is by definition rank of F, and hence rank of F is this difference. So what have I written? Yeah, this difference. So the perp is somewhat interacting naturally with a given bilinear form. Anyway, whatever that means. And with this, I want to end this lecture. As usual, like, comment, share, subscribe, and I'll see you next time.